Alright, now we're going to look at some more examples of systems, 2x2 systems. And you can see that the first two examples are indicating that they're from the review. And in both cases, you'll notice that the system of equations is already set up that both equations are in standard form. Both equations in standard form. It says solve, it doesn't say to use a specific method. So I'm going to probably go with the elimination method. And I kind of like the idea that these are exactly the same amount of x's, 1x and 1x, for the first one. However, the signs are not different, so I am going to have to deal with that. I'm going to take the top equation, I'm going to multiply by a -1. Every term, both sides. The opposite of x plus 3y equals -8. Don't forget the right side. Happens all the time. This one I'm going to leave exactly the same because that way the x's are all set up to cancel out. If I go ahead and add the sides as is, I have 10y is equal to -20. I'm going to divide both sides by 10. I have y is equal to -2. So I know that my answer is something -2. Take the y value of -2, go back to either one of these equations. I'll just take the top one. Careful with your sign. I have x minus 3 times -2. Does that equal 8? Or equals 8, I should say. That's going to be x plus 6 is equal to 8. Subtract 6 from both sides, I'm going to get x is equal to 2. So it looks like 2, -2 would be my solution here. 2 minus 3 times -2, that would be plus 6, that works. 2 and a -14 is -12, that works. This is a good looking answer. Again, when you have a single answer like this, it is the system is said to be consistent and independent. Down here, everything's lined up, maybe not as nicely as the fact that these have the same coefficients, but at least the signs here are working for me. One's plus, one's minus. I'm going to have to multiply through to get this to have a excuse me, to have a least common multiple here, 2 and 9 of 18. So I will multiply this one through by 9 and I will multiply this one through by 2. 63x plus 18y is equal to -36. 4x minus 18y is equal to positive 36. So you can see that the 18y's are going to cancel. I get 67x is equal to, that's kind of nice, I get a 0. Now students sometimes kind of panic when they get a 0 like that because they think they've made a mistake. 67x equals 0 only if x is 0. So that's an okay value to have. My x value is 0. I'm going to plug in here into either equation. I'm going to find the y value that goes with it. I'll just take the top equation here. 7 times 0 plus 2 times y is equal to -4. So divide by 2, I have y as -2. Let me kind of check here. 0 and a -4, yep. 0 and a positive 18, that looks good. And again, a single answer here, so it's this system is consistent and independent. Now I haven't done an example up to this point anyway, you can kind of probably expect it coming now, where we get an inconsistent system or we get a consistent system that's dependent. So we're going to look at these two examples over here. Now this first equation, I kind of like the fact that the y's have opposite signs, but so do the x's. It really doesn't matter which one because I think I can do this just by multiplying one of the equations by a value. So I've been getting rid of the y's, it seems like most of the time, although I did get rid of the x's here. I'll go after the x's. I'm going to multiply this by 3, and this one I'm going to leave the same. I'm going to get 9x, it's so convenient when they're already in standard form. 9x minus 3y equals 6. Don't forget to multiply the constant, and over here, this stays the same. And it looks like, yes, that my x's are going to cancel out. But not only do the x's cancel out, the y's cancel out. So I get 0 on the left side, I have 10 on the right side, which is clearly a false statement. It's a contradiction. That's to tell you that this system doesn't have an answer, that this system is inconsistent. These two lines, if you were to graph them, would be parallel lines, and so it is the empty set for the solution set. You can tell that because both variables dropped out and you were left with a false statement. Clearly this is false. Okay? And this again is called an inconsistent system. Now down here, this equation already has the variable x isolated, so I'm going to use substitution. I haven't done that one for a while. So I'm going to substitute 5 minus 3y, this part right here, right into the x. And that will eliminate the x variable. So I have 2x, or excuse me, I should say I have 2 times this, 5 minus 3y, let me write that down, 5 minus 3y, okay, plus 6y is equal to 10. So I've made my substitution. I have to simplify, distribute. I have 10 minus 6y plus 6y equals 10. You'll notice there are no x's, but you'll also hopefully notice that the y's cancel out as well, kind of like what happened up here. Both variables disappear, but this time 10 on the left and 10 on the right. This is a true statement. That means that every point on the line is a solution because these two equations represent the same line. If you were to take this equation, divide through by 2, and then isolate the x on the left side, it would be identical to that. So since both equations represent the same line, every point on the line is a solution. Now, here's where I differ with some of the textbooks and some other instructors. Some teachers will just write infinitely many solutions. Well, that explains how many there are, but it doesn't really tell you what the solutions are. Remember, I said every point on the line is a solution. So here's how I would suggest that you write it. And it's a little old-fashioned, but the set of all ordered pairs x, y, such that, the bar means such that, and then write down either equation, it doesn't matter which. I'll take the top one, x equals 5 minus 3y, and then the brace. This is telling me every point on the line. That's what this is saying in a roundabout way. So now that we've seen examples of the inconsistent system and the consistent dependent system, and lots of examples of the consistent independent, we're ready to apply this to some story prompts.